Welcome to the Virtual Foundry podcast.
Hi, everybody. Welcome to the Virtual Foundry podcast. This is Volume 4, Episode 4. Today is Tuesday, March 14th, 2023. The time is 1:02 p.m. and the temperature today here in southern Wisconsin is a very chilly 24 degrees Fahrenheit. That's -4 for you Celsius users. Lots of fours in the intro today. It's very chilly for mid-March, but we're looking for some lovely warmer temperatures in about 10 days or so as we get closer to springtime. Today, we're going to be talking about the origins of FFF Metal. I'm Tricia Cease, president of the Virtual Foundry, and with me, as always, is Brad Woods, founder, inventor, and all-around science guy. Say hello, Brad.
Hi, everybody.
Now, Brad, we call it FFF Metal, Fused Filament Fabrication. This style of 3D printing is also known as FDM, or Fused Deposition Modeling, and also BME for Bound Metal Extrusion. Now, Smart Tech Analysis, in their Market for Bound Metal Additive Manufacturing 22 report, said that in 2022, the bound metal additive manufacturing market, the one that we're in, is evolving at a pace faster than any other technical segment. Another stat reported by 3dprint.com, bound metal 3D printing to make $54 billion in metal parts through 2030. Now, any company focused in FFF Metal uses that same basic three-step process: print, debind, sinter. We're all starting with metal powder, encasing it in some kind of binder. Then we're printing, we're removing that binder, and then we're sintering those metal particles together. Now, how did this three-step process get established in the first place? We're going to take a look into the past. We're going into our way back machine, all the way to 2015, 8 years ago. Now, Brad, walk us through your earliest experiments and your development of FFF Metal.
Right. So this started, that's a PrinterBot Simple on the left there. These were one of the earliest accessible consumer grade 3D printers. And this thing, I think it sold for about $250. It was a Kickstarter project. The guy that did it hoped to sell 10,000 of them, wound up selling 1 million of them. And it really kind of, it had a pretty interesting effect on consumer grade 3D printing. It was a very exciting period. But a friend of mine gave me this and said, you got to try this out. So when I got that little printer, it was actually a box of hundreds and hundreds of parts. It took me quite a long time to get it to put together. And I had no idea what 3D printing was conceptually, but never, this is the first time I laid hands on it. And so it took me a couple weeks to get it put together. It took me another week to get a successful print. And when I did, my first thought was that it's just plastic. It needs to be something more interesting than plastic to find a solid application in industry or just about anything else. And there was nothing available for metal 3D printing at the time. They were out there, EOS had one on the market, and some of the other laser bed type strategies, but they were prohibitively expensive and prohibitively even to the people at the very high end of the market. They're just, they're $1 million and up. So there was nothing anyone could, like me, could touch that would let me work with metal 3D printing.
Now, and what is this globby creation here?
That was the precursor to my journey into metal 3D printing. The Virtual Foundry, I've actually used it for over 20 years, and it started out as a method of making 3D objects by electroplating, electroforming, and different methods of breaking down metal, basically ways of making sculpture without having to melt copper. So that's a chunk of copper in the background there.
All right, continuing on.
So about this time, I decided to get a little bit more serious, and I moved to my basement shop, and I set this up. I think I operated here for maybe the first year. Probably the first, I don't know, probably the first 10 kilos or so of metal, of the metal polymer filament that I made were made in my shop here.
Now we can see this photo timestamp says February 17th, 2015. That's the date that you loaded it up into your Google album, but you were actually working on this earlier than that in 2014.
Yeah, it was, there's no hard edge. I mean, there isn't one day that I just started working on it. It was a segue from working with the other method I described with electrolysis, but I'd also been experimenting with precious metal clays, which I didn't fully understand at the time, but they're a form of powder metallurgy. And what they are is it's quite literally copper blended with rice flour. And the rice flour gives it roughly the consistency of clay, so you can work it by hand. And when you're done with those pieces, you put them in a kiln and you can fire them into a pure metal part. And this is foundational to how I got to where we are now with metal 3D printing.
Now we have done a podcast where we talk about how how FFF metal is similar to precious metal clay. So we'll link that in the video here.
Yes. So my first problem was how I was going to make some filament. And this is a concept. I didn't invent the concept. Boy, I wish I could think of the guy's name, but this was put out as just an open architecture, just a freebie open source system where you could make an extruder out of essentially a drill bit and some pipes and some parts that I scavenged off my car.
So this was your first extruder in your first attempts to get this powdered metal and thermoplastic binder into the filament shape.
Correct. So this is the first time I actually took some commercial polymers. Like I ordered PLA from MatureWorks and ran it through this machine. So that was the first opportunity, or the first time that I actually melted plastic and started blending it with metal powder.
Now, we've been looking at this photo here this morning. I asked, what is this rock with a belt? Somebody else thought it looked like a loaf of bread. It kind of looks like a hamburger. What is happening here?
That is an amazing little kiln. Paragon sold these in the 80s. And my dad was into glass work, and I actually bought this for him so he could do glass fusing and things like that. I bought it when I was probably, I don't know, 12 or 13. After he passed, this made it back my way, and then I wound up doing all of our early experiments with this kiln. So this kiln, like Tricia, we can go back. There's the owl statue.
Yeah,
that was done in this kiln. So it looks dumb and kind of silly, but it's incredibly powerful. And it would actually hit 2,400 degrees. It would start to fall apart at that temperature, but you could get there. What I did is, next to it, there's a little temperature controller that I ordered. So I hacked together my own programmable temperature controller for this primitive kiln. The next step was months and months of failures. I have so many of these, I can't imagine how many are boxed up. But each time it would get a little bit more interesting. I would get a little bit closer. It would have better metallurgical properties each time I took a step forward.
science has a lot to teach us about how we handle failure. In science, a failure is a learning opportunity. In business, a failure is a learning opportunity. So that is a sidebar about how much science can teach us about how we view failure in our own lives.
Yeah, and this, I mean, some people describe sort of my method of development as having a hacker mentality. And I come from a background of writing computer code. I started writing computer code when I was 11. And at that time, there was no one to learn from. So the only way you could get through and learn new things was to hack at it, fail, do it again. And that's very much the mentality I brought to this project. I probably failed in every way that you possibly could, and that's how I eliminated the bad ideas. But like I said, I mean, there were times when I would go for weeks without moving forward, but I'd always get just enough of a success to say, okay, we're moving in the right direction. This can work.
Yes. What are we looking at here? What are the components of this picture?
That is an early bronze piece. So the process that we publish, telling people how to sinter our material, has evolved over time. We've simplified it. Early versions of it, involved handling red hot crucibles that we threw into buckets of water to quench them, which clearly we couldn't expect the whole world to work with the material in this way. So my mission at this point was, after we started getting some success, the mission became, how do we simplify this and make it accessible to a greater number of people?
So the dark part in the middle is the actual bronze print,
Yeah.
and the
Yes.
white part is whatever you had encased that print in.
Right. An early version, in the first version of this that we published, we called it, one of our users dubbed it the magic black powder. And essentially it was plaster blended with carbon powder. So the carbon was sacrificial to consume the oxygen, and the plaster was there to help the piece hold its form.
So we still do those two things with our process today. We're providing part shape support and oxygen management. We just do it through a much more friendly, accessible process today.
Yes. This was one of the early glimmers of hope that I was describing. Because sometimes they come out looking pretty dark and you wouldn't know if there was a success till you got them cleaned up. And this one, when I took the photo, I must have been very excited.
So another very early origin, as again, another photo that you uploaded in 2015. So it was taken at least then or before. So very early prototype success here of the process.
Right. That date is likely the date that I took the photo. The camera should have time-stamped it. Yep. Yeah, that was my new Nikon. So yes.
Nice.
And then moving forward, here's another one, just a more of a success. What you can't see here is that the top of it is a complete fail, but the bottom of it is
well, you leave that part out of the picture.
Right. But the bottom of it is a complete success. So again, the process wasn't complete, but it was definitely, the concept had definitely been proven by this point. Same here, there's a chunk of bronze going from fail after fail to success after success. This is glass. So, right, so this was January of 2015. My early observation was that this technique will work with anything that can be sintered. I mean, whether it's an element or a compound, it doesn't matter what it is. As long as it's a solid and it can be sintered, we can make it into a 3D printing filament. And to prove that, and the reason this is gray is it's because I smashed up some beakers on my cement floor in my home shop. So it got a little bit contaminated with concrete, but that is broken Pyrex. All right, so February 2015, this is when I filed the first patent. So at this point, it became a provisional patent, and I staked my claim in time there. The actually granting it, I think it was 2019 when it finally came through. Yeah, so it was, it was a 4-year process to get this thing patented.
I appreciate your note here that someone promptly spilled coffee on your patent application.
Yeah, it might have been me.
Now, this
And
is a drawing that you included in your patent application. Tell us about this.
yeah, so this is artwork from the patent, and this explains what I was envisioning at the time. So in figure 1, the black spots are metal particles. The white space around it is a thermopolymer. And it's that simple. It still works exactly the same way. It is just particles bound up in a thermopolymer.
So we get it into a shape using an FFF style 3D printer, but really the method that you use to get this material into a shape is inconsequential.
Correct. However, you can get it there. You can form it by hand with 3D pens. You can manipulate it with heat, like a soldering iron or something like that. Or you can even injection mold it, which is very interesting. So this is the day I went from, or roughly the time period anyway, that I went from my homebrew extruder up to a commercial one that I bought off of eBay. It was incredibly exciting.
Yes.
At this point, I had just finished the Kickstarter campaign, so I had some cash on hand, and this is where some of that cash went. I bought this antiquated extruder, and it's still the one that we use today, though most of the parts have been replaced. But the core extruder is still the same device.
I enjoy your note here as well, where you write, I believe I've wrapped my head entirely around the scope of this project. Now, 8 years later, looking back at that comment, do you think you had your head wrapped around the entirety of the scope of the project?
No, I do now, but we'll see how I feel about that in a couple of years.
Well, yes, every phase brings us new information and a new exciting continuation into the progress of the technology.
Right, and it's scaled and it's grown into different areas, so it's become much more massive than just us. Oh, so right. So also there were really no machines for manufacturing this stuff. So I used my hobby in microcontrollers and such to build various industrial controls for things like our puller, uh, yeah, like the machines at the end of the line. The downstream processing equipment on the extrusion line is
For
all,
actually manufacturing the filament line.
yeah, and this is still what we use today. This is one of my examples of an earlier, much more challenging procedure. This is Jeremiah pulling a red hot crucible out of a kiln and quenching it. And in there is the trophies for the 3D printing industry awards. We bit off a bit more than we could chew. We probably could have pulled off making 2 or 3, but we committed to 23, and it was brutal, but we delivered.
So we talk about being able to make metal parts in your lab, studio, classroom. So thank goodness we've moved away from this quenching procedure to that more friendly style of sintering, providing that part shape support and oxygen management.
Yeah, and there's been a huge amount of refinement to the process and the printing. So many people have contributed, and so many people have shared the results of their experiments with us. I think we've come a long way in the last few years. These are the trophies that we shipped. They were striking, and it was a challenging shape. The really bulky piece at the very top had a tendency to want to break off. So if I were to do it again, the shape would be a little bit less complex.
We have a podcast that talks about that trophy as well. It'll be linked in the video.
All right. Okay, so then this is just me trying to prove the concept with other materials. So this is a chunk of stainless steel, done in exactly the same way as all of our other materials. The only difference between stainless and, say, copper or bronze is the temperatures that it's sintered at and some of the sintering parameters. But manufacturing it is the same, printing it is the same, everything up to that point. It doesn't matter what the material is. And this is kind of a cool example. Maybe you can talk about this, Tricia. The group that is, we make a moon dust simulant into a 3D printing material.
Yes.
And this is an example of one of the crazy things that I didn't see coming when I started this project. So we have people come to us and say, will you make this into 3D printing material for us? And we've done this for NASA, and we've done this for a few different companies, but the moon dust one is the most interesting.
Yeah, so keep an eye out later this year for the release of basalt moon dust simulant filament. So you will be able to print with a moon dust simulant, just like that mimics the materials that you would find on the moon itself.
Yep. This is sent to us by a user. It's another piece of steel that they 3D printed. Same here. This is a part. It actually moves. I should have separated it, but those are each a different part, all centered as one, but they move independently of one another. So again, a user-generated stainless part.
So now we're moving along through time. This photo is dated 2019, so we're seeing the progress made in the technology here.
Yeah. By this point, we're pretty well refined. This is a part of the extruder for a 3D printer. So this is 2019. Yeah.
Yes.
No, and then so this is relatively new. This is
Yep.
sent to us by one of our users. So this is just, people are making parts and using them. It's really an exciting period. We're gaining speed. People are understanding what we're talking about. When I started this project, very few people, it was very difficult to explain. It's much easier to explain. People are now more familiar with 3D printing.
Yes.
And some of these general concepts like sintering.
This particular piece is Inconel 718. It was printed, debound, and sintered by Drew Turner, one of our partner innovators. Drew's done a lot of work with our full catalog of materials, and he is getting some beautiful pieces out of his process. You'll see some social media about this piece coming out very soon. So Brad, the filament process that you created offers the advantage of an open architecture system, meaning you're using the hardware of your choice. It offers a thermal debind so that you don't have to use any chemicals in the process.
Yep.
And it offers the ability to influence every step of the process. You have full flexibility and control so that you can get your part just how you want it. What resources did you use to come up with this 3-step process in the beginning?
Possibly ignorance, maybe. I started knowing what needed to be done, but not knowing what to do. And during this time, there was some information available on metal injection molding, but really not a lot. Most of it was owned commercially and really not shared with the public. So I was able to get some tips there. I didn't invent the term debinding. That existed, way before, but applying it to this application was completely novel.
You've talked about borrowing from or using that hacker mentality to borrow from other industries to put all of this together. You mentioned MIM, metal injection molding. You've also mentioned precious metal clay. So looking at the process that material uses to lend a hand to the process that you created.
Yeah, and at this time, as I was just starting, there was a couple companies that made 3D printers that worked with precious metal clay. They would essentially water it down and then put it in a syringe and kind of try to print it that way. And it was very, very similar to what I was doing. But the reason I didn't like it is that you had to buy a special printer for it. So all of these things are designed to be used with equipment that is easily accessible and not specialized for this technology.
Yes, so I know that philosophy was very important to you in the beginning, as well as looking for that binder that will debind thermally. So
Yeah.
not needing to use a chemical wash step or any of that, or an extra debind step. Really, the part is going to go in your kiln, work through a heat process for that debind, and then go into a heat process for the sintering cycle. The majority of the materials that we have in our catalog today don't need a special atmosphere. You're debinding and sintering in a common kiln with no special atmosphere requirements. So it's a very accessible process.
Right. And on the debinding side of things, traditionally at this point in metal injection molding, for example, it was they call it a catalytic debind, where you're using very dangerous chemicals like vaporized nitric acid, things like that. But even the ones that don't go that far, where they just soak in a chemical or something like that, the problem is that you produce and consume huge amounts of organic solvents and things like that. So then you have waste, large amounts of commercial waste to deal with. So that was the thinking behind the thermal debind, just keep it simple.
So Brad, one more quick trip into the past with a photo of the first article that was published about your technology in August 2017 by the Wisconsin State Journal, which is right here in southern Wisconsin. It's the newspaper published in Madison, Wisconsin, talking about your invention and the convergence of accessible, inexpensive metal 3D printing.
Yep.
So that's a fun one. If you are interested in reading this article, you can see it on my LinkedIn profile, Tricia Cease on LinkedIn. So Brad, just a word of congratulations to you. It's very exciting to be a part of this project, and really incredible to think about how what you started in your basement in 2014, 2015 is now going to be producing 54 billion parts in the next 8 years. I'm sorry, $54 billion worth of parts in the next 8 years. It's really incredible. So congratulations to you.
Thank you. Yeah, the naive side of me thought that this was going to happen 7 years ago. So it's starting to catch up with my vision.
Great. Brad, I do have one more very important question for you before we wrap up today.
All right.
Why are elevator jokes so good?
I don't know.
Because they work on many levels.
Nice.
Hey, listen, everybody, if you've got a cool project you want to showcase in one of these podcasts, reach out to me at info@thevirtualfoundry.com. If you have a question you'd like us to do a deep dive on as part of the FFF Metal process, again, reach out to me at info@thevirtualfoundry.com. Be sure to check us out on social media, LinkedIn, Twitter, Facebook, Instagram, Reddit, all of the TikTok even.
Yeah.
Check us out there. We do have a user communication platform called Discord. So I'll include links to all of that in the video description. So you can communicate, talk with others about their process and see what FFF Metal is really like. So until next time, happy printing, everybody.
Thank you. Nice shirt.
So in the meantime, until